Hi, everybody. Thanks for joining us today in our 25th meetup by Kaggle's Meetup Delhi NCR. We hope that all of you are doing well and staying safe in these tough times. Today, we have Louise, who would be talking about embeddings, generation, and uses in NLP. In our 25th meetup, she is a Kaggle competitions master, and we look forward to worth learning experience from this session. So, thanks, Louise, for joining us today, and the stage is all yours.
Hello, Ian. Hello, everybody. I'm very happy to be joining you today. So I will be making a presentation about embeddings and more particularly an application on the Kaggle actuarial loss competition. So, okay. So welcome, everybody. So my name is Louise Ferbach. I'm Kaggle Competitions Master, and I'm also Data Science Ambassador for the HP and NVIDIA AI. And right now I'm just starting at SCORE, which is a global reinsurer where I'm doing data science too. So feel free to reach out to me about any questions regarding this presentation, regarding Kaggle or past works. I'll be more than happy to answer you. You really should favor LinkedIn to join me. And yeah, I'm very, I look forward to hearing from you. So today I'll be presenting a wide overview of what embeddings are in NLP. So NLP is natural language processing. Embeddings are word vectors that we use in our models because obviously models are not very good with words. They work with numbers and particularly with vectors. So the first part of this presentation will be dedicated to word representations, how we generate them, what properties we want them to have, and how we can use them. Then I'll be moving on to text representations, because if we have vector representation for words, we would also like to have vector representation for text. So either just some phrases or full sentences or even full documents. This has very wide range of application for document classification, etc. And finally, I will end with a few hints for Kaggle competitions. So first of all, how do we represent the meaning of a word? Actually, the meaning of a word is a more complicated concept in itself that it can seem at first. So obviously, the idea represented by a word is its first primary objective signification. For example, the water was boiling. Everybody knows what water is, what boiling means. So here, every word in this sentence has a very fair and very straightforward meaning. That's the same for the second example. The firefighter ran out of the house. His pants had caught fire. So all words here account for their primary objective signification. However, the principal struggle we have when we are trying to get vectorial representation of words is that words don't have a single meaning. Actually, there are very few words that have only a single meaning. Most of them can be used in a figurative sense in a very wide variety of contexts. So for example, if you take the sentence, he was boiling with anger, we have the same word boiling as we had in the first example, but it doesn't mean the same thing. So the source of the signification here is the same, but here it's used in a figurative sense. And we would not like our model to think that a person has become in a liquid state at 100 degrees and is actually boiling. That's really not what the meaning here. So we also have context where it's not at all a figurative sense. It's just a proverbial phrase or a small song or something like "liar, liar, pants on fire." So it has nothing to do with either pants or fire. It's just a proverbial expression. It's funny. And another challenge here is that this colloquial phrase is playing on a rhyme between liar and fire. And for a model, this would be very difficult to understand. For us, it's very obvious because we hear languages, but obviously an NLP language doesn't hear what it reads. So how could we try to translate this idea of a rhyme, of playing with words, to a model? You also have the problem of some words having very, very different meanings. She was not feeling very well. They were trying to dig a well. It's the same word, but it's totally different meanings. So how can we represent this in the embedding of the word well? Do we want to have two different embeddings? One that would represent the idea of good, one that would represent the idea of a shaft. But that's not a very good idea, because it would be very complicated for words that have a lot of meanings. For example, good has so many different meanings, you cannot have different embeddings for every one of them. It could mean well, I'm good, I'm well, healthy, he looks good, he looks healthy, beneficial, it would be good for him, tasty, this pudding is good, etc., etc., etc. It goes on. Good is one of the words that has the most different possible meanings. We have the same issue with well, as we have seen previously, and with boiling. So here with boiling, the idea is more of a figurative sense, whereas with well, it's pure homonymy. An even more difficult challenge in NLP is with homophones, homographs, and more widely jokes. I think most of you know that when you learn a foreign language, the most difficult thing to grasp and the very last thing you are able to understand are jokes, because it really requires a very, very, very deep understanding of the language, of phonetics, etc. The example I have put below is a dialogue that has been made between Google's AI Mina and a human. And this dialogue is actually very impressive because the AI is able to make jokes. Actually, she makes two jokes, these dialogues. The first joke is that horses go to Harvard. So you have the joke between Harvard, and hay, which is a horse-related word. So actually, I am not native English speaker, and I had to research the two jokes here to be able to be sure that I fully understand them. So the knowledge that the model is displaying about phonetics, about words and their significations and interactions is very, very impressive. The second joke, you can see it, is we are trying to steer it elsewhere in the last sentence. So it's here playing on a homonym of steer, directing, and steer, which is beef. So it's very, very, very impressive to be able for a model to represent that kind of interactions between words in the language. Another issue that is very important to regard is the size of the vocabulary you use, because obviously the wider your vocabulary, the more embeddings you will have to compute. So the definition of what is your vocabulary is a very important issue. So the vocabulary nowadays, which has the most words, is the English language. It's not because it's a particularly complicated language. It is not, compared to other languages which are far more complex. It's more that it's an international communication language, and also it's widely used in research, scientific innovation, etc., as the standard default language. So when you have new words that are invented, usually they are invented to represent a new thing that has been invented. And mostly the word is invented in English because that's the language of research, international communication, etc. And it's not automatically translated in any other language. So that's why English has grown to be the language with the most words. So research by Harvard and Google in 2010. It was very, very, very wide research on all books available, all the internet, and has found a little more than 1 million words exist in English. So that is huge. And especially since you consider that it's growing by several thousands words a year when new words are being invented. And so it englobes a lot of words that are not really necessary if you want to build a model. For example, the process of inventing new words is very easy. You just have to take a fantasy or science fiction book, and you will see that most of the time the authors invent a lot of words for a lot of imaginary things that they are putting in their works. So it's very easy to use new words, but you don't really need them in your language if you're not working on that type of subject. So another study is just looking at the Oxford Dictionary. In the Oxford Dictionary, you have around 600,000 words, but these encompass a lot of words that are very ancient, that are not in use anymore, that have been long since forgotten. You don't really need them if you are building, for example, a model that is scraping Twitter. And you could restrict it to about 170,000 words, which are actually being used recently. And lastly, if you consider adult native speakers, so they are the people who you can consider to have the wider vocabulary, and they have vocabulary that is usually between 20,000 and 35,000 words. It depends a lot on their activities, their interests, they like to read, on their education, on their professional activity. It depends on a lot of things. But it's actually very, very, very restrictive. So deciding which vocabulary you use is very important. And most of the time, NLP models are not based on words, that are based on tokens, which are lower word level. It is particularly useful when you are working, for example, with internet data, because the internet is very, very, very good at inventing new words. For example, you could write something like "it is huge" with a lot of "you." Actually, it's just the word "huge." It's not a new word. So you would like it to be decomposed so that it can be in tokens, so that it can be considered similar to "huge." So to sum things up, to get word representation, so of course context matters a lot, because your model will learn the signification of a word from what context it finds it in. For example, if you want to take the embedding for the word owl, and you train a model, let's say, on the Harry Potter books, maybe the embedding you get for owl will be very related to the postal system. Whereas if you train it on a biology textbook, it will be more centered on maybe eating habits, sleeping patterns, etc. High dimensionality is very important because we have seen that words have very complex interactions with each other. They have a lot of different meanings. They have a lot of different double entendre. You could, for example, play on not only the meaning of a word, but also its sound. We have seen it with Harvard. So it's important to have that kind of information that is represented in the word vector we use. And finally, diversity of text resources is fairly important if you want to be able to grasp a very wide overview of the meaning of a word. You have to be able to find it in a lot of different contexts. So how can you get word representations? So the first naive idea that you could have is you take vectors which are the size of your vocabulary. Let's say you take the average English adult. He has 20,000 words in his vocabulary. So you're saying, I will take 20,000 dimensional vectors. And for each of the word, I will put a 1 on an axis. So every axis will be supported by one word. So obviously, it's not working very well. Why? It's huge, because you wouldn't want to have at least 20,000 dimension. You could hardly go lower than that, and that would make it impossible to process by your model. That would make your model very, very, very heavy, and you could not build very performing models. Commonly used word embeddings have around some hundreds of dimensions. Usually it's between 100 and 400 dimensions. Another issue here is orthogonality, because if you do this, every word will be orthogonal to all others, and that's not what you want, because you want to be able to reflect some similarity, and you would like that similarity to be reflected by the angle between vectors. Like the more similar two words are, you would like their vectors to be very near in the vectorial space. That is to say that they would have a cosine similarity that would be very near 1. And here, for example, you have cat orthogonal to dog. It's not very good because cat and dogs have a lot in common. They are both animals. They are both very human related. They are pets. So you would like them to have a similarity, not to be completely orthogonal. And the last issue is that all vectors are normalized. So you have no gradation whatsoever, no collinearity, and you would like to have, to be able to use the coordinates on each axis to reflect an importance. For example, you would like to have something like the vector for small, which would be more or less collinear to tiny, because you have just a gradation idea between the two. Same for bad and worse, etc. So what are the requirements to get efficient word embeddings? So we would like them to be large enough so that they are able to capture multiple meanings, as we have seen previously. Is very important to have complex vectors which are able to reflect the whole complexity of the meaning of a word, but they need to be small enough so that you can use them to feed to models that will actually be computable. And so it's a bit tricky to find the good dimensionality. Usually models have around the hundreds of dimensions. So about density, words are discrete. It's a discrete space. It's not like images. Images are in a continuous space, but for words, obviously, it's a discrete space. So your vectors would be in a discrete space, but yet we would like each axis to represent an intensity, to have an idea of gradation. And lastly, as we have seen previously, we would like the cosine similarity of two vectors to be able to give an idea of the closeness of meanings between two words. And lastly, we would like to be able to reproduce some conceptual operations in this vectorial space. We would like to have some conceptual relations between words that could be translated in operations vectors. For example, to have the vector man plus the vector royal, which would be more or less the vector king. Same for king, and you add the vector young, which would give the vector prince, etc. That's the kind of operation you would like to be able to find in your embedding space. So let's just look at a toy example. If I just take, for example, a two-dimensional space, and I say the first dimension will be the idea of feline, and the second dimension will be the idea of a house. So these two vectors are orthogonal. Is it a problem? Well, not really. They don't have much in common, feline and house. So it's not so shocking that you take them orthogonal. Then how would you represent the vector for cat? So it's a feline. So you would take a 1 on the first dimension. And it's somehow related to the idea of a house, because a cat is often in a house. It's a pet. So you could put 0.5 around the house dimension. And then if you want to represent tiger, so it's still a feline. But why would you put a negative value on the house axis? Well, it's a wild animal, so it's a bit of the contrary of what you would associate with the idea of home, and it's definitely not the kind of animal you would like in your house. So maybe we can put 1 and minus 0.5, and then if you look at the cosine similarity between these two vectors, it's 0.6. So you could say cat and tiger are 60% similar. It kind of makes sense conceptually, because they are animals of the same family. So it's a nice properties we would like to find. So now I'm going to present the most widely used model for computing word embeddings, which is Worldtovec. It has been introduced by Mikhailov in 2013, and it's state-of-the-art embeddings computing. So it's very important to understand how it works. I'll just give a general idea, general overview, and I will not go into the mathematical details. It's not that important right now for what we're trying to do. So in Worldtovec, the vocabulary is fixed, meaning if you train your embeddings on a given corpus, and then you give it a new word which it has never seen in his corpus, it will not be able to compute an embedding. So most of the time for this kind of events, we have an UNC token unknown, which is an embedding for unknown words, which is used in that event. So every word will be represented by a vector of given size. It's initialized at random. And then what do? We take our corpus on which we're training, and for each position T in the text, T is the center word, and you take its outside words within a window of given size. So you could take, for example, here in the image, it's a window of size 2. So you take the 2 words left, the 2 words right, it's the context words. And what are you trying to do? You're trying, given the center word, to predict which words are in the context. Here, the problem is I have my center word that is into, and I would like to be able to predict that the context words for into will be problems, turning, and banking crisis. So how do we compute the probability of the word at position, for example, -2? Given the central word, it's just a cosine similarity between the 2 vectors of embeddings. So, for example, the vector for into, scalar, the vector for problems, normalized. That is a probability of problems given into. And we keep adjusting the word vectors, so we optimize the word vectors so that this probability is maximum. We want the cosine similarity to be maximum, and we do this for all words in our vocabulary. So this window here is sliding on all the text. Then next step, we will take banking, and we will try to predict into, crisis, etc., etc. So what's important to notice here is that this is position blind. It doesn't have a position notion. The process would be exactly the same if it was turning problems into banking crisis, or if it was banking turning into problems crisis, even if it doesn't make sense. The only thing that matters is which word is at the middle. But you could understand that it still gets a grasp of some position because of the sliding window, because at the previous step, when turning was the central word, crisis was not there, and there was another word that was there. So he kind of is able to get a sense of the order thanks to the sliding window. So there are 2 variants for Worldtovec. The first one is to predict outside word given the central word, so it's just what was here. And the other method, which is continuous bag of words, is just the contrary. It's exactly the contrary. So you take, sorry, what happened? Sorry. Excuse me a minute. Excuse me a minute. Okay. Okay, so the second method, which is a continuous bag of words, basically it's the contrary. So you take the context and you try to predict the middle word. So you would say that the context is problems turning, banking crisis, and you would try to predict into. It's just prediction of WT knowing the WT -2, T -1, T +1, and T +2. So now what concretely happens? So I have tried to compute a Worldtovec in the actuarial loss competition. I don't know if you've seen it. So the purpose of this competition was to predict claim amounts given some information about work accidents. So we have some information about worker age, his salary, etc. And we have a small text description of the accidents. So here I just completely dropped all the other data, and I just focused only on the claim descriptions, and I will be trying to get a grasp of how we can have an idea of the claim amount, what it costs. So it means the gravity of the injury, given the description of the injury. So here I have trained the Worldtovec model on these claim descriptions. They are very short sentences of the type you can see on the right: lifting tire injury to right arm and wrist injury. And if you look at the most similar words to a given word, so what it is, it's the word vectors that have the highest cosine similarity to a given word vector. It is able to give you an understanding of what the model thinks are similar terms. For example, for fall, the most similar words in the vectorial space I have computed are stumbled, fell, which makes sense, falling also, injuries also, but you also have some strange words. For example, irrigation, what does it, and it's almost 58% similar to fall, which is surprising. And it's actually a very good hint that your corpus is not wide enough. It's too small. It's very important to have a very varied corpus so that you're able to fully understand, to fully grasp the meaning of a word. Otherwise, you're very subject to overfitting. For example, here, just maybe by chance, he often found the word irrigation next to fall. But that's really not what we would like. You have the same for right. For example, right is very similar to left. That's actually that actually makes sense. But you also have some interesting relations with part of the body, like elbow, femur. So it's probably broken right femur, broken elbow, and same for left. You have the kind of same body parts, but you also have some very surprising words. For example, canopy. So then if you try to represent the words you have computed in the first 3 dimensions of a principal component analysis, this is word cloud, so you only see the outliers actually. Stripper is kind of an outlier, meets also. So now we have been able to see how we get word representations, but most of the time we are more interested in text representations for sentences or even for full documents. So that's what we are going to see now. So the first intuitive way of getting text representations would be simply to average all the word vectors you have in your sentence. So if you have a sentence of n words, for each word you have a word vector, and you just take the average component wide of these vectors. So the sentence embedding would be the average component wide of the word vectors for I equal 1 to n. Or you could take a projection of that average on a lower dimensional space. So the problems with these methods, first, it's order blind. So if you just take an average of words in a sentence, the order of the words doesn't matter. And sometimes it makes a huge difference in meaning. For example, we are in the context of work accident description. And if you take fell on his knee, injured his back, and fell on his back, injured his knee, if you just take the average of word vectors, they would have exactly the same embeddings. These sentences would be embedded in exactly the same vector, but it's actually very different, because probably an injury in the back is going to be much more, is going to have much more consequences than an injury of the knee, and is going to cost more. So it is a limitation. And the other problem is that it's word importance blind. For example, if you take the cat and the dog, here the keywords are cat and dog, but they would have the same weights as the and, which are very generic words, which you would find in any sentence, and they don't bring any information in the sentence. So that's also a limitation. What you could do with regard to this is do term frequency, inverse document frequency weighting. So you just basically weight your words. So instead of taking a ground average, you take a weighted average, and you weight based on the term frequency, but inversely to the document frequency, so that it's a real, it gives a real sense of the actual importance of a word. For example, words like the, and and are very, very frequent, but they are also found in every document. So they would not have a big weight. So what are the results? Here, I have tried to, here, what does this graph mean? So I have computed my word embeddings on the claim descriptions corpus, as I have shown previously, and I've just basically averaged them. No weighting, no projection, no anything. And then it's projected on the first two principal components. So for those who are not familiar with PCA, principal component analysis, the idea is that you try to find the two orthogonal vectorial dimensions that explain the most of the variance of your vectors. That is to say that they bring the most information with regards to the variance of your word vectors. They are able to separate your word vectors in the optimal way. So here, the points are projected on the space of the two principal components, and you can see that actually the embeddings are fairly able to separate claims with regard to their cost. The color is just the cost of the claim, so it's a proxy for severity, because something that is going to cost a lot is obviously more severe than something that doesn't cost much. And you can see that you have two clusters that are fairly separated. So it's interesting that our embeddings, averaged word embeddings, have been able to grasp an idea of the severity of an accident, given its description. So here, these are it's exactly the same, except that it's not the embeddings that I have trained myself on a corpus. It's pre-trained embeddings. So left to right, it's embeddings trained. It's 300-dimensional embeddings that have been trained on whole Wikipedia. Center, it's still 300-dimensional embeddings, which have been trained on all of Google News. And the third one, it's 200-dimensional embeddings, which have been trained on the whole of Twitter. So you can see it's different, but they are still able to separate claims fairly neatly. So it's very interesting that they are still able to grasp an overall idea of the severity of an accident. So another way to compute sentence embeddings or text embeddings, which is a bit more complex, is to use Tovac. So it has been introduced still by Mikolov. You have two ways of using this model. The first one, so the two of them are very similar to Worldtovec. In the first way, which is distributed memory model, what do? You just introduce a new token, which is a paragraph token, and you put it at the beginning of the sentence. So it's kind of a new word, and you try to predict the next word given this context, which has been augmented by 1. And you train your paragraph vector just as you train your word embeddings. And in the end, you end with a paragraph token which has been trained and which is kind of a summary of the overall meaning of the text. It's able to act as a kind of memory of the meaning of the text to predict the next word. And the second way is basically reverse. So you just take paragraph vector, and given that paragraph vector, you try to reconstruct all the words that were included in this paragraph. So it's distributed bag of words. It's unordered. So what has been the result of this method? It has not yielded very significant result. This is what I have obtained when I have trained it on the claim and the insurance claim. So you can see it's not able to separate anything. It's clearly not an appropriate method to this problem, but it's still a very interesting method that has been proved very useful in a lot of other contexts. So the third possible method to get text embeddings is just to use the encoder part of a transformer that has been trained on a tool task. For example, you just take a transformer, let's say BERT, and you train it on a sequence-to-sequence tool task, like, for example, paraphrase or just classification tasks like paraphrase detection or document classification or topic modeling, etc. And then when it has been trained, then your transformer is able to, the encoder part of the transformer is able to map an input text into a latent space, a latent vectorial space, and then the decoder takes the representation in this latent vectorial space and adapts it to give an output that is relevant to your task. So we're not interested in the decoder part, we're only interested in the encoder part because it is a mapping from an input sentence into a latent space. And that will be the vector representation we'll be interested in. So this graph is actually very nice. So how did I get it? I just took Roberta, so it's robustly trained version of BERT, and this one has been trained on, and this one has been trained on paraphrase detection. And I have used it to get sentence embeddings from my input sentences. So here I'm using glove embeddings, not using pre-trained embeddings. I'm using glove embeddings, and I'm just using the encoder part of the Roberta to map them into the latent space. The latent space is 768 dimensional. In most transformers, the latent space are always 768 dimensional. So I just do the same process as I have done previously, projecting it into the first two principal components so that I have an idea of the most accurate representation of the variance between my vectors. And it gives these two clusters that are fairly separated given the ultimate cost claim. So it's a very nice result. So now a few hints from Kaggle. So if you're looking for text resources for your projects or Kaggle competitions, or to train your own embeddings or anything, if you're looking for some high quality text, there are the Gutenberg project. It's very interesting because it has all license-free, copyright-free literature works, all books. So it's huge. Obviously, you have a lot of literary works you can train on. So it's very useful if you want to train word embeddings. It's also good for translation because most of classical literature works have been translated in several languages, at least 3 or 4. You also have Archive, which is a big database. It's interesting for problems like topic modeling, topic classification, because you can train them to be able to classify documents with respect to their theme, or it's also good for getting embeddings for rare technical words. You have Wikipedia, of course. Wikipedia, I should have put it first. It's very, very, very big. It's high quality text. Well, there are errors, but not so many of them. And also what is interesting about Wikipedia is that it is very, very wide. You have all kinds of topics on Wikipedia, from biology, literature, history, everything you want. So it's actually excellent to be able to train embeddings that will be able to fully grasp a very, very wide overview of the meaning of words. Wikipedia is also very good for translation because sorry, I'm messing things up. It's not good for translation actually because pages are not translated. They are rewritten in different languages, but they're not a translation of each other. If you're looking for internet quality text, so you have the whole internet that is out there waiting for you. There's Twitter, Reddit, Yelp if you want to do reviews, classification, positive, negative. Reddit is good for a lot of internet quality text. Twitter is good for short sentences. And lastly, for translation, so I have said the Gutenberg project, it's huge for translation in the main most common languages. You have also reduced texts, which are good for rare languages. If you're looking to train a translation model on rare languages, oral languages for which they are very, very few written resources. Most of the time, the only written resources you will find are religious texts, because they are the only books that anybody has ever bothered translating in some languages. So it's mainly the Bible and Quran, but you have others. And finally, for some languages, you can use low text, because for countries that are bilingual or multilingual, usually low text have to be translated in all of the official languages. So that gives a huge database, because laws are obviously public. So you have the European Union low text, which are interesting because they must be translated in all languages of the European Union. You have other countries like Canada, etc. So that's useful resources. So on Kaggle, most of the time, so that is my personal opinion, I have found that training your own embeddings is often not a good idea, except if you really have a huge data set that is really, really huge. Otherwise, you will always miss something. You will always miss an idea of a word that has not been found in your corpus, and you will have some overfitting issues. So it's not very helpful most of the time. But what is very often good is to improve model performance by customizing embeddings. So either you start from pre-trained embeddings like Glove on Wikipedia, and you fine-tune it on your text data. That could be good to get a more accurate representation of your text and not losing the complexity of meanings that can be found in much wider corpus. Or you can customize them by mixing them together. For example, this here is the first place solution in the QnA insincere question classification. So first place was by the zoo. This is the solution that was shared by Psi. And what you can see that the embeddings they used 70% of Glove, and they added 30% of program embeddings, which are some paraphrase trained sentence representations. It's interesting. So what is the embedding as input here? So for every word in a sentence, you will have its embeddings will be the sum of 70% its standard Glove embedding. So Glove is just, for those who don't know, Glove is just the Stanford trained Worldtovec. And it's also 30% of program, which is an embedding for the sentence. So for each word, you have an idea of its own embedding, and you also have an idea of the overall sentence embedding. So if you take two different sentences which both have the word cat, the word cat will not be embedded in the same vector because they are in different sentences, and the 0.3 will change. And it has won them first place, so it's very interesting. So thank you very much for your attention, and now I'll be taking questions.
Yeah, sure. Thank you, Louise, for such an awesome presentation around the embeddings and the text resources at the end, as well as the hints for how to deal with Kaggle competitions and other stuff that were really useful. Like we have like a question. So with I am flashing the question on the screen. Is the future of NLP revolving around using as big as vocabulary as possible and training as big as model as possible?
Okay. So I think for the first part, no, and for the second part, yes. Why? Because for vocabulary, I don't think that getting bigger and bigger vocabulary is any use, because most of the time on most of the tasks you do, you don't need a million words vocabulary, because there are very, very ancient words that are completely out of fashion, that nobody has used for centuries. There are a lot of words that are so specific to a context that you will never find them anywhere. Just take some science fiction invented words. So it's really not useful to extend your vocabulary to millions or billions of words. It's of no use at all on general tasks. But for model, yes, it's true that models tend to get bigger and bigger and bigger and to get more performing. I think everybody knows about GPT-3 from OpenAI, which has not been released to the public because it's actually thought to be too dangerous, because it's so good at creating fake news or that kind of content. So it's true.
Yeah, got it. So another question is, how can we check the robustness of our models? Like how they will handle real world data?
So you can. So there are several ways to do it. You can robustly train your model with adversarial examples. That's a way. There are a lot of things that exist around adversarial training in NLP. It's also important to pre-process the data set correctly, because most of the time when the models have an issue, it comes from the data, because they reproduce what they have seen in the data. For example, when you have artificial intelligences like, for example, OpenAI GPT-3, that you can just manipulate them to speed up racist stuff, and it's very easy to make them say racist stuff. Why? Because they've seen it on the internet and they've been trained on the internet. So most of the time it's about the data, correctly processing the data. And
Got it. So one of the question that like a community member asked, it was like while someone is starting with natural language processing, like the basic, person who is just starting NLP, how would you suggest, like what are the steps that they should take before diving into this embeddings and other stuffs?
So NLP is a very, very, very wide field. There are a lot of things to understand. And when you're starting, it's true that you can get a bit lost in the middle of everything. So actually, I learned NLP by the Stanford YouTube channel, because I have the NLP course on the Stanford YouTube channel, which is fully available with all resources, notebooks, slides, and everything are fully available. And it's an excellent way to get started, because it's a step-by-step process. He starts with word embeddings and he moves on to some elementary models and everything. So it's good to learn things in the right order. And also don't try to jump right away on the most state-of-the-art models. Like maybe don't start with BERT, maybe just first try to understand what a recurrent model is, LSTM, RNN, how does it work, what can you do with it, and then move on to more complicated models.
So yeah, got it. So like starting from the basics, then taking little
Yeah.
steps to move forward towards advanced things. So yeah, like in case you are a book, like you learn NLP from book stuffs, like book related stuff. So like, would you suggest any books, or even if any resource or blogs that you would love to share that you
Yeah,
recommend?
I have a book. I have an O'Reilly book on NLP. I think it's called NLP with PyTorch. It's excellent because it's very excellent because it mixes theory, step-by-step theory in the right order with all the right basic explanations, math and everything, and mixes it with code all the time in PyTorch, which is, I think PyTorch is an easier framework to get started with than TensorFlow, because you can do more hands-on manipulation. It's more NLP-like. It's a bit more intuitive. Well, that's my personal opinion. So this book is nice. Otherwise, you have a Kaggle NLP course, which is good. As I said, also Stanford videos. If you go on their website, they have a lot of notebooks that are very guided step by step. So it's excellent.
Yeah, got it. And it's like as you have time working with the industry too, like industry based NLP problems. So like in industry, the data that we have, or the messiness in the data that is used for NLP processes is too much messy, right? So how like what would be your suggestion towards dealing with that? Like though it requires a lot of pre-processing and other stuffs, but what would be your suggestion behind those dealing with messy data in the real world for NLP use cases?
So from my experience, like the first reflex you would have when you have messy data and you want to build a model on it, the first reflex you would have would be to try and clean your data so that it's easier to get processed by models. That's what I used to do. And it took me some time to realize that actually it's really not a good idea, and that's not what you should do. Why? Because if your data is messy, like its messiness is an overall characteristic. Its messiness is an overall characteristic, and it's important because all the data you have is messy and all the data you will have is messy, and there is information in it. And if you try to clean, you're gonna scoop over some of the information, and that will be a problem. It will not be real world compatible, and you're going to have some bugs, you're going to have something in your cleaning that you will not be able to process. So actually the model should be adapted to the data, not the data should be adapted to the model. And you should try different architectures, try different maybe embeddings that would make it better. Actually, tokenization can be a huge help in frameworks where you have, like, for example, internet data, which are with a lot of mistakes, misspells, and everything.
Yeah, got it. Thanks for the answer on that. And it's like a lot of folks who start with NLP or machine learning as such, they try to skip those basic processes like pre-processing, feature engineering kind of stuff. Like somewhere the basics are lacking in those the things. Like as we move ahead, we definitely understand that the requirements of feature engineering and those basic stuffs are really really important. So what would be your suggestion on those things? Like how, like from your experience working with data, like how much do you think that those things should not be missed, like feature engineering, hyperparameter tuning, and other stuff?
Well, of course, it's important. From my experience, when I was started, I was so excited to get to building impressive models to have good results. And actually, when you're just started and you don't have enough understanding of what you're dealing with, you will try to get started with a big model. You will get stuck, not understand why, and then you will have to go back to the basics of feature engineering, feature importance, just plotting some stuff to get to really understand what's going on. So even if you're excited and you don't want to spend too much time on it, you will come to a point where you have to, because the only way to understand why your model is not working or why it's not doing what you want it to do is to really understand what's going on, what's the data, and what you need to do.
Yeah, got it. Completely agree with that. And like a few of our community members were interested, like what's this domain of actuarial science and how where data science and machine learning fits into it.
So actuarial science, for those who don't know, it's just mathematics, statistics, probabilities applied to the insurance field, the risk area in general, and it's mostly in insurance. So this competition, it was about insurance loss claiming, so predicting losses for work accidents. So you were an insurance company, you are trying to predict losses. Actuarial science is basically statistics, and machine learning is basically statistics too. There are just different ways of doing them. So they are very, very linked. Now there is more and more machine learning taking place in insurance as in any other fields of the industry. It's really a trendy topic right now. So you have a lot of interesting stuff to do.
Yeah, insurance definitely has picked up in this COVID times, like medical insurance and those things taking a boost at a large scale today. So, like related to that, like maybe if that question is clear, like what is the final purpose of embedding claim description in actuarial science? Like,
Okay, so in this competition, the final purpose was to predict the claim amount. So I've just take one part of the data and done some illustrations on it for the purpose of this presentation. It's not exactly what the competition was about. It's helpful for the competition because if you are able to grasp an understanding of the gravity of a claim, you will be able to get better at predicting what it will cost. So these embeddings combined with the other features we had been provided, which were, I don't know, the age of the worker, its salary, etc., would be able to be fed to a model and then predict the ultimate claim cost.
got it. So another last question, maybe like regulatory things definitely comes into picture. Like when we work with data, right? Like we have certain regulations out there for data privacy, and like certain types of regulations come around healthcare data and financial data. So like how do you see this, like regulations and the data and kind of stuff, like from your experience, just a touch upon on that.
It's very tricky and very important. Why is it tricky? Because if you use data and you feed it to a model, even if the model is very, very complex and does a lot of very, very, very complex transformation on your data, still it's here. Still he has learned from it, and still there will be adversarial attacks that are able to make it spit it out. So actually making sure that the data you use to train your models is freely available, that you have consent, that you are free to use it, is extremely important. Privacy is really big stake. So I think it's a big challenge.
Yeah, got it. Thank you, Louise, for joining us today in our 25th meetup. It was really a pleasure to learn from you, and we really thank you for your patience to answer the questions so well. And like the points mentioned were truly to the point, and I hope that those would be useful for the community members. So thanks for joining and thanks for sharing the knowledge. Thank you. Like we are
Thanks
closing
for
the event.
thanks for inviting me. Thanks a lot for this meeting.
Thank you. Thank you. Bye.